Hello guys, I will continue today with some problems related to signal discretization and illustration of the Shannon theorem. So this is the first problem where we have a signal in continuous time which has a Nyquist frequency equal to 250 pi rad per second. And we have another signal yt which has a Nyquist frequency equal to 300 pi rad per second. We are asking for the Nyquist frequency for the following signals: a multiplication of xt times yt, a multiplication of x of 2t by y of t over 5, and here x of 2t, and at the end the multiplication of the first derivative of x and y with respect to time. To answer these questions, we will note x of omega and y of omega to be the Fourier transforms of xt and yt respectively. So now the product in time, xt times yt, has a Fourier transform which is equal to 1 over 2 pi x of omega convolution y of omega. When we do convolution in the frequency domain, okay, so the highest frequency which is contained in this convolution product, it is the sum of the Nyquist frequency for each signals xt and yt. So the answer here is 550 pi, which is the sum of the two Nyquist frequencies. To answer the second item of this problem, so here we have a signal x of 2t. I think it's the third item, but we have started with this one because the second one can be concluded from this basic question. So the Fourier transform of x of 2t, it is 1/2 x of omega divided by 2. So when we have a coefficient in time at, x of at, where a is greater than 1, okay, we will have a time transformation in the frequency domain to be 1 over a, which gives 1 over 2, with a factor of 1 over 2. 1 over 2 will not affect the frequency of this spectrum. So we will have here x of omega by 2. So what is happening to x of omega over 2? Assuming that x of omega is the Fourier transform of xt, now x of omega 2, we will have a dilatation of this signal. It means the frequency, the Nyquist frequency, will increase by 2. So this is why the Nyquist frequency of x of omega by 2, it is 2 times the Nyquist frequency of xt, of x of omega, which gives 500 pi rad base per second. To deal with the product of the two signals, x of 2t, y of t over 5. So here we have a coefficient a which is greater than 1, and here we have a coefficient a which is less than 1. So in the frequency domain, we will have 1 over 2 pi, the inverse of 1/2, the inverse of 1 over 5, which gives 5 over 2, x of omega over 2 convolution with y 5 of omega. So here we have a dilatation in the spectrum of x, and here we have a compression in the spectrum of y. This is why the highest frequency contained in this y of 5 of omega, it is 1/5 the 300 pi. And the highest frequency contained in x of omega divided by 2, it is 2 times the frequency of x of omega. So here 2 times gives 500 pi, and 1/5 of these gives 60 pi. Now convolution, it means we will add the two frequencies of this and this, which gives 560 pi rad per second. The last item of this problem is asking for the Nyquist frequency when we multiply the first derivative of x by the first derivative of y. We know that the Fourier transform of the derivative dx over dt, it is j omega x of omega. And the Fourier transform of dy over dt, it is j omega y of omega. Okay? So now the Fourier transform, okay, look like the simple multiplication of the two signals xt times yt, because the spectrum will not change the maximum frequency contained in the spectrum of dx over dt. It is the same spectrum as x of omega. And the same for dy over dt. So this item, it is exactly the same answer of the first item, which is the sum of the two frequencies, which gives 550 pi rad per second. In this problem too, we have a signal xt, which is exponential minus 2t times the step function ut. And we would like to make a sampling of this xt such that the aliasing error is less than 1%. 1% of the maximum magnitude of at half the sampling frequency. So we will start by composing the Fourier transform of xt, and this gives the value 0.5 by 1 plus j 1/2 of omega. So the magnitude of this, it is 0.5 divided by the square root of 1 plus omega squared divided by 5. We would like that the maximum frequency is reached. The maximum frequency reached for this spectrum, it is when omega is equal to 0, which gives 0.5. If we tolerate 1% of this maximum magnitude 0.5, it means we are speaking about an error of 10⁻⁻3. So here we have the magnitude of x of omega. Okay. This we will equal to 10⁻⁻3 to get the omega 0, which is the half of the sampling period. The half of the sampling rate. Right. By solving this, we will get omega 0 equal to 200 rad per second. But the Nyquist rate, it is 2 times omega 0. It means it should be 400 rad per second. So the sampling period should be greater or equal to this value, which is 400 rad per second.